will start at kind of a block level view of the product. Okay. So this is an internal block diagram of the PoE5 that shows two adjacent RJ45 ports. As you can see, there's a data path that allows Ethernet data to move from one RJ to the next, and that is a certified to a category 6A data path. So you can use it at whatever data speed you want, 1 gig, 2.5 gig, 5 gig, 10 gig. Whatever you want to put over that is completely up to you. It's a completely analog passive data path. So there's nothing besides circuit board and relays in between those two things. So if you want to pass data between two ports while you're testing PoE, it allows that. Internally, there's kind of two power paths. So there's the main pair and the alt pair, which is what we refer to them as. The IEEE refers to those as alternative A and alternative B. And those are the 1, 2, and 3, 6 pair, and the 4, 5, and 7, 8 pair. They're completely independently configurable if you want to do dual signature testing, where you have one power pair as, say, a class 3 and one as a class 2, separately negotiated. I'm not sure whether or not your PSC supports that or not. Some do, some don't. But if it allows you to do dual signature, if you're doing BT testing or 4 power pair testing, we have a single signature relay, which allows only one PD controller internally to advertise its PoE class, and that lets you do a 4 power pair load. So technically class 5 and above are required to be power pairs. Excuse me, 4 power pair loads. That's the hardware signature. That's the actual power over Ethernet negotiation. So when it does, when you determine how much power a given PD wants to have, that's the actual class negotiation. Usually when you have you connect a PD device to a PSC, you have the initial voltage detection where the PSC goes through and looks for the 25 kilo ohm signature to say, hey, there's a PD at the end of this pair, and then it goes through detection of what class the device is, so how much power it wants to have. The allowable thing is, so that like class 8 gives you the up to 90 watts from the PSE available, all the way down to class 0, like 10 watts. But it's that whole negotiation process that lets the PD say, I want this much power. I said we're a completely passive device, so if you need to do LLDP testing, you'll need to emulate that externally by putting a link partner on, say, here and doing all the LLDP negotiation that way. This is purely the hardware level or layer 0 negotiation for power. The data link is always present. Only the power is not off. And if you do, if for example, like the PD is set for a class that is outside the PSC's capability, it should negotiate power I mean, this is all depending on you guys' software implementation, but it will negotiate power and either demote the PD to a class or ignore it altogether. If it is set outside that and it's demoted, you can read the bits as to what it was demoted to out of the out of the PD. Going back through the block diagram, so for 4 power pair connections, we have the signal signature that allows like class 5 and above to be negotiated, and for connection check from the PSC to pass. That's where after the negotiation, there's a separate, it switches over to the alternative power pair and looks for voltage appearing over at the main pair to verify the 4 power pair load is there. 60 watts per pair, 100 watts total per port. Cat 5 is fine. It's the wire gauge internal to the cable that really determines that, but we don't really have any way to detect that. It'll just be lossier that you might otherwise see. But like that's a test implementation detail that you guys need to figure out. But it's not. We don't care. We'll draw whatever you tell us to do. So we've got the PD controller and the class selection logic that lets you set classes, maintain power signature. PoE5, it's our 5th generation tester. We've been making PoE testers almost since the dawn of PoE. So let's just do like a really quick setup to kind of like maybe get a feel of how you might want to run a test. So down at the bottom, I have the menuing system for a PSC demo board. So you can kind of see from the PSC's perspective what's going on, which is probably a lot closer to what you as developers will see anyway. But so we can kind of start off by just inputting the detect OK command. And that sets the 25 kilo ohm detection resistor to either OK or low, and where low is an out of spec resistance, so your PSC should not continue the negotiation process. Got to set our signature. So let's do a 4 power pair class. So that turns on the single signature relay that we saw earlier, and allows us to do classes 5 and above, or above 5. Let's set a class 8 class, and it's ready to go now. We just need to decide what kind of load we want to put on it. You can specify load in either watts or milliamps. A lot of people find watts to be a little more convenient. But if you're trying to find the edge of where your PSC like does a load cutoff, milliamps is a lot of times easier because there's not the power noise where the load is servoing around looking for watts. A little easier to sneak up on things, but let's say 70 watts. So that tells us that each pair, the main and the alt pair, alternative A and alternative B, are going to draw 35 watts each. That was what each of those 60 watt loads back in the block diagram will be doing, for a total of 70 watts. If you want to specify offset loading, where you have pairs that maybe aren't exactly matched, that we allow that too. So you can make imbalanced loads if that's something you want to do. So yeah, so that's the kind of minimum setup you need to run any given test. So now we can connect, and that engages the actual load. There's relays in between the port and the load, and the connect command is what closes those. Yeah, it's just straight RJ45s. We offer an 8-port and a 24-port version. All ports are allowed to draw full capacity, so you can pull, in theory, 2400 watts out of a device. it's connect 1 or connect 0. Right now I'm using the generic versions of the command. If you just issue a command without a port argument, it applies to all ports in the device. This one's an 8 port. But if you only want to work on one port, you can specify a port argument. The argument can be just directed at a port or at all ports. Disconnected all 8 ports. Now I only connected port 1. So I issued the P1, which is the port 1, and then it will only connect that one. Class determines what powers are allowed. So like you've got maximum 15.4 watts at class 0, and then you've got 90 watts at class 8 with steps in between. So this right there is how much it's policing. That's what the PSE is saying. Don't go above, if power draw goes above 90 watts, shut it off. So you can see it. We got a power cut because we went above what the policing was set to. So a port has 2 pairs in it. We can do 60 watts on each pair. It will in dual pair mode, it will only allow you to draw 100 watts. That's a thermal cutoff. So if you want to measure power, you just use the get command. So get, in this case, get P, and that will tell you what each individual port is doing. So 30 watts per pair, 60 watts per port. That's what it's measuring. Watts are always rounded, and that's partially just because of the imprecise nature of doing power as opposed to current. Also, we round it a little bit because when there's a cable involved, you're dissipating power in the cable, and that when we round it, it reduces confusion as to what's actually being drawn. We have the current measurement, where you can get a much more accurate picture of what the current draw is, which is what the get I command does. We also have a voltage measurement circuitry that gives you a voltage to the nearest 1/10 of a volt at any given time. So pair 1, pair 2. You can use the PSE command, and that gives you the bits that were set during negotiation. And there's a table in the manual that lets you go through and decode what the bits are. But these are the outputs for that. If it's on page 29 of the manual, lets you go back and see if there's a power demotion case or something. But it's easier, a lot of times easier to see that on the PSE side of things. But you also can validate that any given pair is power good. So that tells you that there's power good on both pairs of these 2 ports. So we already kind of went through like, if you want to overload a pair. So we have another command called short that lets you test whether or not your PSE can detect that there's a short before negotiation. So you can see it detected a short. You cannot use short when there's power good, just because that can cause damage to both your PSE and to the PoE5. But we do support the short command when power is off, so that you can detect shorts in the line. And you can see it goes back to open there. We also support a low detect a low detect resistance, where it provides an out of spec detect resistance. And depending on your PSE, if you have asymmetric loads, or you can set loads such that load only appears on one pair, or goes out of balance, or things like that. You can draw any amount of power available, regardless of class. So you can make sure that when you go outside of a class boundary, it catches that. We also support the minimum power signature. So if you don't have a load on, it will go into the low power keep alive current. You can change things around to drive whatever conditions you guys need to test out of bounds, for instance. So I'll set that up one. So we've got a 90 watt limit on this port. The demo board is a PSE. We just have PD simulation. We go above our power limit there, it faults. So you can put it into an overload situation for the class. So it went outside the limit, and the power policy on the PSE was set to 90 watts, so it cut it. We can adjust that, and you can see it at other levels. But yeah, that's programmable on the PSE side for almost everything, as far as I know, because it's a policy register rather than a hard limit. Most of our customers script all of that externally, either using Python or Expect or another scripting language. We do offer the ability to set a favorite configuration. You can save that configuration to the EEPROM and recall it at will, but there's only one slot for that. But if you have a default configuration that you like, you can always just save it and recall it without having to reissue all the commands. The load is dynamic, so even if you set it at one value when you start the test, you can vary it all over all the time with no limits. We have some basic Python scripts libraries, but they're just for interacting with it. We don't have canned tests. And since it's a command line interface, it's very easy to script.